presentation, I would like to invite Professor Dr. Hiroyuki Hama, a professor from Research Center for Electron Photon Science, Tohoku University, Japan, to giving a lecture on the topic of Introduction to Research Center for Electron Photon Science at Tohoku University.
Okay, so Prof, I'm Hiroyuki Hama from Tohoku University. And, first of all, I'd like to say that thank you so much to invite this meeting. But maybe I have some misunderstanding of the purpose of this meeting. So today's slide, my slide is just an introduction. Introduced my university and my laboratory. It's okay. Really? Right. So Tohoku University is located Tohoku area in Japan, and so established in 1907 and as a third national university. And this in Japan, maybe the four big universities: Tokyo University, the Kyoto University, they come here, and Osaka University also big one, and this Tohoku University is almost comparable with the Osaka University. This guy is the president of Professor Hideo Ono. He's a specialist of the spintronic science. Okay. Oh, this is we have maybe the 86 national universities in Japan, and this is the budget per year. The Tohoku University now is a third of the budget, but the total budget from the government is getting lower and lower, like this one. And so, yeah, it is absolutely true. Japan is getting very much poor. Yeah. Okay. Oh, sorry. So before talking, I introduce myself. My background is nuclear physics and PhD in 1987, and I was working at the Ubisoft facility. And at that time, I'm doing the research work for the ring beam dynamics. And the first low alpha experiment was done by our ring. And FEL on the ring, the shortest waves record at that time, we record. And also another thing is the dual cavity system and ring impedance calculation and helical undulators developed. And after moving to the Tohoku University, I got the FAL prize and the original thermionic RF gun I made, and the compact 50 MeV Linac TX is the homemade facility is working very well, and also femtosecond bunch for coherent radiation can be possible, and I developed the Maxwell equation solver, and another theoretical research work was done. And I was the director of the laboratory for 6 years, and I'm always looking for the money, like this dog. Okay. Yeah, it's a very hard time for me anyway. Okay. So maybe everybody knows that Sendai Tohoku University is located here, And now is a 3GB light source is developed nearby, actually inside of the Tohoku University campus. And this is around here is the center of the earthquake of 2011. That was a very big earthquake. We suffered a lot of the damage. The other major facility, accelerator facility in Japan. This is a earthquake center. It was very, I remember so much. Okay, anyway. So the history of our laboratory. The Research Center for Electron Photon Science. So this name is a bit confused because many people misunderstand this laboratory is for the synchrotron radiation, but it's not true. So it's confused words. Electron photon means photon comes from the electron. Only the meaning is only that. Okay. So the short history of this laboratory, 1966, this laboratory established and 300 MeV LINAC. I think it's one of the biggest electron accelerator in Japan at that time. And the short pulse neutron generation. It's, there are many neutron facility, accelerator neutron facility in the world, but this our laboratory starts this pulse neutron from the accelerator. Experiment is started. This guy is try to generate the neutrons from, and also another topics is in 1988 was first observation of coherent synchrotron radiation. And 2013 to complete 50 MeV test accelerator TX project, and we restarted the user providing the beam for the users. This is a 1.2 GB stretcher. It's a booster ring. Okay. Then, so AAPPS bulletin. This is Asian Pacific Physics. I don't want to forget. And this journal of this one, we can find our laboratory. Then details of the Elph laboratory activity can be found in the journal. This we have actually we have 4 accelerators here. Then I'm going to talk about our equipment. So this is a 1.3 GB. It's upgraded after the earthquake. The 1.3 GB synchrotron ring and this injector for the beams, the ring, and the new beam line to measure the proton radius. And this is a high power LINAC. It is modified from the older LINAC. And the energy is just maximum energy is just 60 MeV, but beam power is maybe the number 1 in the world. In Japan, okay, but very high power machine. And this is a control room, and this is the particle counter for the hadron physics. Okay, this is a T-ax. So we have measured the 5 groups. It's one group. The Professor Onishi is he is the leader of this group. They are doing the hadron physics quark hadron physics by using 1.3 GeV BSC ring and also this hadron counter, and their collaboration with Osaka University. And, the Professor Suda is now doing the experiment for measuring the proton radius. I'm going to explain later, but so this machine is a high power machine and can produce radioisotopes. And this is our accelerator, 50 MeV TX. This is to produce a very short electron bunches. And also the accelerator and the beam physics is here. And another group is condensed matter nuclear physics. It's a normal temperature fusion reaction they are studying. So, and the engineering group here. So this is one synchrotron and the high energy gamma ray coming from the internal target wire, the carbon wire. And the beam, storage beam is hit the carbon wire, and the brainstorm gamma ray is coming from the wire. Then the scattered electron, the energy is measured inside of the dipole magnet. Then we can know the energy of the high energy gamma ray. And this is a high power machine here, and this machine makes a radioisotope, and the RI production by nuclear photoelectron, photoreaction, and radiation chemistry and activation analysis, medical application. These are by using the short-lived radioisotopes. It's now a proton radius measurement project is going on. And on the TX, we are doing the femtosecond beam pulse production and also super radiance from the short pulse electron and variable polarized trias source we have developed. This is outer. It's a high power machine. And we are using the radioisotope and unsealed radioisotope experimental. This is kind of a hot lab. Okay? And we have two gamma ray beam lines in the booster ring. One is here, inside of the extra accelerator hall. And another one is the next building. The brainstorm gamma ray is go through the sealed concrete, and we have gamma ray can be converted to positron electron pair, and it is very much useful for the counter calibration for the particle physics. So sometimes they are using this beam line. So the latest scientific result from the 1.3 GeV BSC ring. So this is the size of the nature. Okay, magnetism can cover this area, and the particle getting small. The QED and the QCD is dominates around this kind of the nuclei and the hadron and a bit of the quark. Then weak interaction is dominated leptons and unified strong theory and here. Well, anyhow, this is the stage of the nature, and our target is around here. Then recently we have found the 6-quark state. It's not familiar, but usually the hadron is made by 3-quark. But theoretically, 6-quark and 9-quark or 7-quark or no problem. It can be consistent. But there is no experimental result. But we found the 6-quark state. So now this is a usual nuclei, and then now 2 hadron is touching very close to. So this particle is made of the 6 quarks. So we need more spectroscopy for this kind of the phenomenon. Yes, from high power Linux, this is RI production. The electron beam is hit the converter, it's heavy metal, and the bremsstrahlung gamma ray hits the target, and the reaction is gamma P on the gamma N or something like gamma, yes, photo reaction anyway. Then we can produce a lot of the radioisotopes. So this is 2017. We made this kind of the one, and 1 gigavector is very high. This RI is used for, is shipped to another laboratory to use radiation chemistry or something. So usually the medical radioisotope is produced by the reactors in the world, but those reactors is getting old, and also a lot of the RI produced simultaneously. But we need more clean production process. So the accelerator is very much important to produce the radioisotopes. So another experiment of using this machine, this is I don't want to say, around 2000, the proton radius was it's measured by the muon. The result was very much different from the electron scattering. So if this discrepancy is correct, everything is changed. Then, so they are going to measure the. Oh, I'm sorry. Measure the. Sorry. Yeah, new spectrometer is installed on the experimental hall, and the precise measurement of by using a low energy beam. Then now they are accumulating the experimental data. So maybe the proton radius is measured very old time, but at that time the data analysis is maybe not wrong. So there is no discrepancy, but maybe the proton radius can be explained by the unified theory. So this is our machine with the TX. This is RF gun, and the 3-meter accelerating structure is here, and the terahertz undulator is here. This is alpha magnet. Then this femtosecond beam and coherent radiation. We can produce 80 femtosecond beam constant steadily. Then by using velocity bunching, the successful observed coherent terahertz up to 4 terahertz. This coherent radiation can be using the beam diagnostics and terahertz imaging, and also circular decroissance for molecular. So anyway, now, 2 or 3 years ago, we have studied about the development of the world's smallest undulator with Professor Shigeru Yamamoto at KK. So this is 20, undulator period, just like 4 millimeter. And the total, so this is the undulator, it's like this one. But this is a 4 millimeter with 20 period. It's a very small one. So, and we observed radiation from this undulator. Calculation here. This is a very interesting innovation, maybe for if you are using the synchrotron radiation. So because we don't need long storage section. It's a very important thing to design the storage. Okay. So now I think maybe the ILC linear collider project is that is just a project, but it will be installed here, the Iwate Prefecture. This is Sendai and the Tohoku University, our laboratory, and now the nanoterrace storage ring is almost completed. It will be open for the user next year. So then this area is very exciting for the accelerator physics, okay, and also the photon science. Okay, that's all.
Well, thank you, Dr. Hama, for the lecture. Is anyone have any questions?
So thank you very much, Professor Hama, for the nice talk and your share. At this slide, ILC is just the project that will take place, that will open very soon, or is still the project?
This project is still alive, but just as a project, the station is, honestly say, is not good.
Okay, so same as in Thailand, we have like a TGEV project also. Yeah, we talk like many years now. Yeah. Okay, thank you very much. Any other question for Professor Hama? Yeah, we see overall of the facility you have. Yeah, we hope that we can talk in detail. So in terms of application that we be able to access or do the research with your facility. Thank you very much.
Thanks so much.